So this is a short talk which I call Ancient Light. And as you can see from the subtitle there, imaging a quasar without a telescope. So this was, if you like, my lockdown challenge. We all know that the universe is vast and the universe is ancient, and we know that large telescopes, including large professional telescopes, have been able to image galaxies that are many billions of light years distant. But the question I asked myself was, is it possible to capture an image of one of these very distant galaxies, one of these very distant objects, without using a telescope? And no surprise, I wouldn't be giving this talk unless the answer was yes. Otherwise, it would be an even shorter talk than Bob had indicated. So don't read this. This is just telling us that professional astronomers have surveyed a lot of these so-called quasars. Now, what are quasars? A quasar is the nucleus of a galaxy that emits so much light that that galaxy is visible from a distance of many billions of light years. So I'm going to be talking about a quasar that I've imaged. If you like, just think of it as a galaxy. It's simply a galaxy with a very active nucleus. It's probably a supermassive black hole, which is producing an awful lot of light from the region around the black hole. This particular survey that these professionals carried out and published last year, one quasar is quite interesting, and this is the quasar. It goes by the wonderful name of J1617 blah 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 blah. Quasars are identified by their number, their ID, which is also their coordinates in the sky. So these two numbers are right ascension and declination. So the fact that the declination is plus 59 something tells us that this quasar is very high in the northern skies and was hence a good target to try and catch from the United Kingdom. And what we're actually seeing here is the spectrum. We see here from blue to red the intensity of light coming from this particular quasar as captured by these professional astronomers. And what is particularly interesting is this biggest bump there, which we see at about 6,500 angstroms. An angstrom is 1/10 of a nanometer. And that's interesting because if we compare this spectrum to the sort of spectrum we would expect from a source which isn't moving, from, if you like, a laboratory-based light source, we would expect that particular bump to occur at 1,200 angstroms, rather than, as we see here, at about 6,500 angstroms. So this peak has moved an awful long way from where we would expect it to be if the source of light for this particular object was not moving. In fact, 1,200, if you look at the scale, blue is at about 4,000, red is at about 7,000 angstroms. So 1,200 angstroms is way, 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 way over to the left-hand side, way beyond the blue, way beyond the violet. 1,200 is in the ultraviolet part of the spectrum. But because this particular object is so distant from us, because it's receding from us so rapidly, according to the Hubble law, which says that more distant objects are receding from us faster, this object has had the ultraviolet light shifted all the way from 1,200 to 6,500 angstroms. We can measure, or we quantify how much that shift is by looking at the shift itself, in this case, the difference between 1,200 and 6,500, so that's what, 5,300 angstroms. We look at that shift relative to the original value. In other words, it's shifted by 5,300, its original value was 1,200, and we call that quantity, that ratio, the redshift, and we give it the symbol Z. So the redshift for this particular object is 5,300 divided by 1,200. It comes out to be 4.3 something. That is a very large redshift, and that tells us that this particular quasar is very remote. But it is in the northern sky, it's high enough to be seen during the summer, and therefore I thought during lockdown, what the hell, this is probably not going to work, but let's try it anyway and see if we can actually catch with a camera rather than with a telescope, can we actually produce an image of this particular object. So I took my camera, I happen to be a Nikon owner, so there's my Nikon camera with a telephoto lens. and I put the camera on this white box. This white box is a star tracker. This particular one is made by a company called Ioptron. Other star trackers are available. It's basically just a box that is motorized so that it turns the camera 1 revolution per day, and hence it compensates for the fact that the Earth is rotating and allows the camera to follow the stars. In order to make sure it's lined up with the Earth's axis, there's a little polar scope on the side that you can see here. And so the idea is you put this tracker on some sort of a tripod, take it outside, point it north and make sure that Polaris is lined up inside this polar scope. Then you know the tracker is lined up with the Earth's axis, and then the tracker simply rotates the camera at 1 revolution per day. The camera is mounted onto the tracker via this little gadget here. In a sense, this is a very small Altaz mount that simply allows me to point the camera at any part of the sky whilst the tracker is doing its business and rotating the camera around. There's the type of camera that I used, and I used a 300mm telephoto lens. Remember, of course, that when we're talking about photography, whenever we quote a measurement like 300mm, we're talking about the focal length. In astronomy, there tends to be a convention that when you talk about a particular measurement, you describe the aperture of the objective lens or the mirror, and you don't think so much about the focal length. With photography, you tend to do it the other way around. You quote the focal length, and in this case, f4 tells us that the size of the front element is about 1/4 of 300mm, so that would be about 75mm in diameter. One thing to note that this camera is not an astronomical camera. This camera, and indeed the lens itself, are the setup that I use for wildlife astronomy. I'm quite a keen photographer as far as wildlife is concerned, and this is the camera that I would use if I was going on safari. For instance, on holiday. Do you remember the times when we used to go on holiday? Yep, okay. So if I was going on holiday and I wanted to take pictures of animals in Africa, this is the equipment that I would use. The equipment has not been specialized, it has not been customized, this has not been modified for astrophotography. That camera and that lens took this picture last year. It is ideally suited for taking pictures of zebras. Fantastic. Can a system that's been designed to take pictures of zebras also take pictures of quasars? That was the question I effectively asked myself. So we have this quasar from its identification number, if you like. That's also its coordinates. So I looked up where that was in the sky, and it turns out to be in the constellation of Draco. Remember, it's at about 60 degrees declination. So Polaris is over here on the right-hand side. There's the constellation of Ursa Minor, and here's the constellation of Draco. And so this particular quasar happened to be quite close to a star. If we look at the actual field of view of my 300mm lens, the dot in the middle is a star that just so happens to be quite close to that quasar. That meant that when I pointed the camera at the sky and looked at the star field on the back of my camera on the little LCD screen, I could see that star. I couldn't see the quasar, much too faint to see the quasar, but I could see that star, and so I knew I was pointing in basically the right direction if I centered the camera on that particular star. It happens to be about 5th magnitude. And then I just needed to take a picture. I put the camera on its tracker outside. It just happened to be outside the front of my house. Unfortunately, there were a few street lights around. Excuse me. So my neighbor also has a floodlight. I tried to get out of the way of that floodlight. And in order that the street light didn't affect the image too much, I simply put a wheelie bin next to the camera to try and shade the camera from the light of the street light. I then exposed for as long as I could, which turned out to be about 2 hours or a little bit more than 2 hours, and it produced this image here. It wasn't a single 2-hour exposure. That wouldn't work for a lot of reasons, partly because of light pollution. It would tend to fog the image. And also, I can't guarantee that my tracker keeps it perfectly aligned for a 2-hour period. So I took a lot of short exposures instead and then added them up in a computer later. So I set the camera to take 30-second exposures. Once it had finished a 30-second exposure, it started another one, and then another one, and then another one. And I simply left it going. took exposures for, I think, 2.5, maybe even 3 hours. I didn't have much choice as to when to take the pictures because this was taken in the middle of July and the sky doesn't really get dark until getting close to midnight. So I waited until the sky was reasonably dark, set it going, and it took images over midnight and up to maybe 2 o'clock in the morning or something like that. It clouded over for some of the time. I just left it running, even though I could see some clouds were coming. Rather than stop the camera, wait till the clouds had gone and then restart the camera, I simply just left it rolling effectively. So I took hundreds of images, some of which ended up being completely blank because of the cloud. Some were spoilt by clouds scudding by. I simply threw those away and kept the good images. It turned out I had more than 200 good images. So that was enough to add together to give me this image. In the middle there, you can see the bright star that I was effectively lining up on. That's the 5th magnitude star that I used as a reference. But the interesting object, the quasar, is sitting next to that star. You can't see it in this image. It's a 20 megapixel camera, so there's 20 megapixels in this. We have to zoom into that little square there to actually see the quasar. We can't see it at this scale. But if we zoom into that region, then the quasar should be in the middle of that image. And there it is. So yes, it is possible to capture a quasar using the camera that I've described, a conventional digital SLR camera plus a telephoto lens. There isn't much there in the sense that that image is barely 1 pixel. Most of the light from the quasar, it looks like I have managed to focus it correctly, most of the light from the quasar is focused into 1 pixel and a tiny amount of light has gone into the neighboring pixels. If we blow it up a bit, you can see what's going on. Most of the light has gone into that 1 pixel, and here, some surrounding pixels, I've made those a little bit artificially brighter by processing the image so as to bring out those fainter pixels, just so you can see what's going on there. But essentially, most of the light from the quasar has gone into 1 pixel in the image out of the 20 million pixels that are in the image itself. So I was very pleased to find that at the end of the day, after doing a little bit of processing, adding up all of these images to get the equivalent of a 2-hour exposure, I managed to capture this particular quasar. But I also noticed, whilst I was looking at that and thinking about what it is that I'd captured there, I realized that this particular crop, the entire image itself, the image that you can still see in the background, covers about 3 to 4 degrees of sky. But this particular crop that I'm showing in the middle of the image is 8 arc minutes by 8 arc minutes, an 8 by 8 arc minute crop. And I noticed by comparing this image with an image taken by professionals that actually there's a few galaxies there, as well as the quasar in the middle. I've caught maybe 10 other galaxies. It's not obvious from looking at them that those are galaxies rather than stars. I could only tell by checking against professional images. Some of them you can see perhaps are galaxies because they look a little bit extended, but you can't really tell if that's a double star or a galaxy. I had to go to NASA archives to actually check. So I figured that if that particular small crop of the image contains about 10 galaxies and maybe 20 stars, then if I scale that up to the full image, my full image, which I'm now labeling as the Barrett deep field, that full image must have captured something like 7,000 galaxies, that exposure. And I thought that was quite curious because the Hubble deep field, taken in the 1990s, captured a similar number of galaxies. There were many thousands, I think at least 5,000 and possibly 7,000 or 8,000 galaxies in the Hubble deep field. And I thought it was curious that a camera and a telephoto lens pointing at essentially a random part of sky can also capture a similar number, many, many thousands of galaxies. Now let's have a think, now that we've decided it is possible to capture that light, let's have a think about some of the numbers involved in how that light was captured. It's possible to convert what I was talking about before, the redshift that's visible in a spectrum, into how far away is the object. So here we've got a plot of redshift horizontally. Remember, the redshift is not in any units, it's how much it's shifted compared to its original value, a particular feature in the spectrum, so that comes out to be just a number. And on the vertical scale here, we have distance, which I've labeled here in millions of light years. One thing to bear in mind whenever you're talking about very distant objects, it's very easy to talk about, well, that galaxy is 100 million light years away, so the light has taken 100 million years to reach us. One thing you have to bear in mind is, whenever you're talking about cosmological distances, rather than simply distances, for instance, within our galaxy, you can't actually measure how long the light has taken to reach you, and you can't measure how far away an object is. The only thing you can actually measure is the redshift. You can take its spectrum and you can work out how much the individual lines or features in the spectrum have shifted towards the red end of the spectrum. So you can measure redshift, but anything else you have to deduce, you have to calculate. So for instance, we know the universe is expanding, and from the redshift we can work out that, yes, if I'm looking at an object with a redshift of this much, let's say I had a redshift of 2 for a particular object, I can work out that I'm looking back in time to a time when the universe used to be smaller. In other words, distances between galaxies was much smaller than it is now because the universe is expanding. And I can calculate, if I understand how the universe is expanding, I can calculate how it's expanded since the light left the object and how long it's taken the light to reach us. And I can also calculate, if the universe is expanding, where that object is now. The light may have left it a long time ago, and that object has since moved on, carried by the expansion of the galaxy. But all of these things are calculated, and they all depend on our understanding of the universe's expansion. And that's why these sort of curves are not absolutely definitive. If we decide that the universe is expanding in a slightly different way than we first thought, then those distances are going to change. The redshift as measured is still the redshift as measured, but the equivalent distance that that object must be will be slightly different if we decide that we've got something wrong. We can only work out what the universe is doing in terms of its expansion if we understand, for instance, how much matter there is in the universe, and if we can measure, for instance, the Hubble constant, which tells us what is the velocity of an object at a given distance. If we can pin down those numbers, then we can pin down these curves. If we've got the Hubble constant wrong, then those curves will shift up or down a little bit, and the distances will change slightly. So just bear that in mind. So let's look at this particular example. This is what we might get if we looked at objects for redshifts from 0 to 6. If we were dealing with the Hubble deep field, we would be dealing with objects all the way down to redshift 5, 6, maybe even 7. But of course, in this particular case, we're dealing with our quasar, which has a redshift of 4.3 and a bit. And if we read off the numbers, these curves I've calculated for our best guess for what we think the Hubble constant is, how much mass there is in the universe, etc. And hence this is the best guess that tells us how we convert from redshift to distance. And for that, we find that for this quasar, its distance when the light left was 4.6 billion. The light has been traveling for 12.4 billion years, and it's traveled a distance of 12.4 billion light years. And the object is now 24.6 billion light years distant. So let's just remind ourselves in words what those three numbers mean. Let's just get rid of the curves and concentrate on the quasar. So the quasar distance from Earth, which didn't exist at the time, the distance from us, if you like, was about 5 billion light years when the light was emitted. So a long time ago, the distance from where we are now to where the object is, the quasar is, was about 5 billion light years. And the light from the quasar has been traveling for about 12 billion years, a little bit more, 12.4 billion years. Bear in mind that the universe is 13.8 billion years old, and therefore 12.4 billion years is about 90% of the age of the universe. The light from this quasar to produce the image I've just shown you, the light has been traveling for 90% of the age of the universe. If we went not from a redshift of 4, but if we look at the Hubble deep field and go to a redshift of 6, that number would be not 12.5 billion years, it would be about 13.5 billion years. In other words, instead of looking back with my camera 90% of the age of the universe, the Hubble Space Telescope can look back about 95% of the age of the universe. For me, 12.5 billion years. For Hubble, 13.5 billion years. That extra billion years of look back time is clearly very expensive. Okay, Nikon cameras aren't cheap, but the price difference from using a Nikon camera to using the Hubble Space Telescope to go from 12.5 to 13.5 billion years, that extra 10% costs an awful lot of money. During those 12 billion years that the light was taking to reach us, the universe, of course, was continuing to expand, and so the quasar was carried along with it, and the quasar is now a lot further away. The quasar is now about 25 billion light years away. Before we move on to the next slide, just one thing to notice. If we say that during those 12 billion years, what's the distance to the quasar? Well, it was originally about 5, and then 12 billion years later, it was about 25. So the quasar distance has changed from about 5 to about 25 billion light years. And it did that over a time period of 12 billion years. It's moved its distance has changed, I should say, rather than moved. Its distance has changed by 20 billion light years over a time period of 12. 20 divided by 12 is more than 1. That means that the recession velocity of this quasar, the rate at which its distance is increasing from us, is greater than the speed of light. Roughly speaking, when the light left the quasar was receding from us at more than twice the speed of light. That is an amazing thought in itself. If we think about the light's journey, this is a diagram. The horizontal axis is distance from us. So there's distance from us 0 up to distance from us 12 billion light years or giga light years. And the vertical scale is the time since the Big Bang. So the Big Bang was in this bottom left-hand corner, and we are in the top left. So there's the quasar. There's the 4.6 billion light years, and the light left the quasar about 1.5 billion years after the Big Bang. And we are there in the top left, that's us, in other words, the here and the now. And I've just noted on the last slide that the quasar is receding from us at about twice the speed of light. So let's see what happens when the light leaves the quasar. One of the most amazing things about the light's journey is because the universe is expanding, and at the time the light left the quasar, the universe was expanding at more than twice the speed of light. The light is trying to get to us, but the universe is expanding at a much faster rate, twice the speed of light. So what that means is the light actually gets further away from us with time. There's the light leaving at 1.4 billion years after the Big Bang. And a little bit later, the light is further away from us. It's trying its best to head towards us, but it's getting dragged backwards by the expansion of the universe. If you like, it's getting dragged backwards for, what is it, something like 2, maybe a bit more than 2 billion years, the light continues to get further away from us. And after about 2 billion years, you notice that this curve starts to turn around, and eventually the light starts to get closer and closer to us. And eventually, after a journey of about 12.4 billion years, when the universe is about 13.8 billion years old, then the light finally reaches us. So it's rather amazing to think of this idea. It's a bit like a swimmer swimming through water. If a swimmer can swim at a particular speed, but the water is flowing and there's a current pushing the swimmer back, if the swimmer can swim at 2 meters a second, but he or she is in water that's flowing the opposite direction at 4 meters a second, then that swimmer is going to be carried backwards, even though they are trying to swim forwards. And it's the same sort of idea with light coming from very distant objects. You can see that if the object is fairly close to us, if the object is only a few million light years away, you don't get this particular effect. You see it when the object is very distant and you're looking back a long way into the past. So that's what the light did on its way to us. If we think about what the quasar did, we have the same point at which the light left here, when the quasar was 4.6 billion light years from us, about 1.4 billion years after the Big Bang. We know what the light was doing, but what did the quasar do? Well, the quasar was continually carried out by the expansion of the universe. So during those 12 billion years that the light took to reach us, the quasar's distance from us continued to increase. And now it's over here somewhere in the top right-hand corner, perhaps just off the slide there. It's now some 25 billion light years away from us. I've shown it as a straight line. That's not strictly accurate, because during the 12 billion years of the light's journey, the quasar velocity, the rate at which the distance to the quasar increased, changed slightly. It's roughly speaking receding from us at twice the speed of light, but it changed slightly during those 12 billion years. So it shouldn't, strictly speaking, be a straight line. It should be a slight curve, but I'm just showing that just to give you a general idea. So finally, I'd like to finish with some prose, which is what I was thinking about when I realized I'd managed to catch the light from the quasar, is the equivalent of the diagram showing the green line there, but written out in words. The light was emitted by the quasar 1.4 billion years after the Big Bang, 12 billion years ago. For more than half of its journey, the sun and the earth didn't even exist. For the first 8 billion years of its journey, the sun and the earth didn't exist. So after 8 billion years, the sun and the earth were born. And it continued its journey for another 4.5 billion years. So the earth formed, life evolved, the light traveled on. Dinosaurs came and went, the light traveled on. In the last million years of its journey, it finally arrived at the Milky Way galaxy. It crossed a few spiral arms and it entered our solar system. In the last few hours of its journey, it finally arrived at Earth, traveled through our atmosphere in a fraction of a second, hurtled towards England, found its way towards the Wirral, dodged a few clouds, entered the lens and hit the camera sensor and produced that image that we saw a few slides ago. Just a pixel, but what a journey. This is a little photo montage just reminding you of what I've said. There's the camera that I used in the bottom left-hand corner, my Nikon camera on a star tracker. That's where I pointed it in the constellation of Draco. A 2-hour exposure gives us the Barrett Deep Field there, the main image in the middle. And if we blow up this region near the center, we get the crop in the top right-hand corner where we see 1 or so pixels indicating the presence of the quasar. So yes, it is possible for a camera that's designed to take pictures of zebras, it is possible for such a camera to capture what I like to think of as a quasar's ancient light. Thank you all for listening.